Section 9.3, other identities. We're going to talk about the double angle identities first. So for this first equation, we have the sine of, let's say, 2x. Now, we can derive the sine of 2x by using our addition identities, because remember that the sine of 2x we can rewrite as the sine of x plus x, and then we've learned the sine addition identity, which states that I have the sine of x and then the cosine of x plus the cosine of x times the sine of x. And if you notice, these two are like terms. We have cosine x and sine of x. So really, we can rewrite this as 2 times the sine of x times the cosine of x. And this is actually my sine double angle identity. So we just derived it. So it's easy to get if you can't remember what it is. Same thing with the cosine of 2x. We can also derive this by doing the cosine of x plus x. And then remember, the cosine identity would be the cosine of x times the cosine of x. And if this is plus, remember in your formula it's minus sine x times the sine of x. And since these are both the same, we can rewrite this as cosine squared x minus sine squared x. So that would be my first double angle formula for cosine. And then the last one we have is for tangent. So my tangent double angle would be equal to the tangent of x plus x. So if we use our tangent addition identity, we get the tangent of x plus the tangent of x over 1 minus tangent x times tangent x. So this becomes, in my numerator, 2 tangent x over 1 minus tangent squared x, and this right here would be my tangent double angle formula. So again, if you forget what these identities are, it's easy to derive the identities. Now, the cosine double angle identity also has two other forms that we use. So going back to the cosine of 2x, we just said it was cosine squared x minus sine squared x. Well, remember that we also have identities for cosine and for sine, cosine squared and sine squared. Remember, cosine squared equals x equals 1 minus sine squared x, and sine squared x equals 1 minus cosine squared x. We learned that before. So if I take those values and replace them into this formula, I have two more forms for my cosine double angle formula. So one of them, other forms, would be if I replace cosine squared with sine squared. So this would be 1 minus sine squared x minus sine squared x. And if I reduce this, I can combine these two because those are like terms. So 1 minus 2 sine squared x. This would be an other form for my cosine double angle. And then one last form for your cosine double angle would be, instead of replacing cosine with 1 minus sine squared, we're going to replace sine squared with 1 minus cosine squared x. So when I do that, I get that the cosine double angle other form would be cosine squared x minus 1 plus, because I'm distributing the negative, cosine squared x. Cosine squared x and cosine squared x are like term, so that becomes equal to 2 cosine squared x minus 1. So that is my other formula that I have. So for this, you want to make sure that you write those down. So right now I have my sine double angle formula, I have my cosine double angle formula, and we did the tangent. And again, you also need to know the other forms of your cosine double angle formula. See, these are other forms. They're not the traditional form for cosine double angle, but we use them a lot, so you need to know those just like we need to know the other Pythagorean identities. Now, from this, we can then also derive our power reducing identities. So For your power reducing identities, you can take your cosine double angle formula to help you do this. And we're going to use the other form. So if I have the cosine of 2x is equal to 1 minus 2 sine squared x that we just learned, well, the power reducing identity would then be for sine. So if I solve for sine squared x, I would take the 1 and subtract it to the other side. Then I would have to divide both sides by -2. So when I divide both sides by -2, I end up with, and I'm going to change the signs of my numerator, so 1 minus cosine 2x over 2 equals sine squared x. So this is my sine power reducing identity that I can use. So I can also get one for cosine. Now the cosine one I'm going to use comes from the other form of my cosine double angle formula, which was 2 cosine squared x minus 1. So if I want to find the cosine power reducing identity, I use this one because I'm solving for cosine. So I would add the 1 to the other side, so I get cosine 2x plus 1 equals 2 cosine squared x. I would divide by the 2, and when I do that, my cosine power reducing identity is equal to cosine 2x plus 1 over 2. So again, this is my cosine power reducing identity, which we also need to have. So that's how you derive those two, by using your cosine other forms to help you get that. And then we can use what we just found for the power reducing identities to help us find the half angle identities. Now, the half angle identities, that means we want to take the forms that we just found, and for this, I don't want it to be squared, so if I get rid of that squared, I'd have to take the square root of both sides. So the sine of x would be equal to plus or minus the square root of 1 minus cosine of 2x over 2. And because it's called the half angle identity, instead of taking the angle x, we're going to take half of that. So that would be the sine of x over 2 is equal to plus or minus the square root of 1 minus, now I'm taking half of this instead of 2x, I'm going to do 2x divided by 2, which is just minus cosine of x over 2. So this is where we get the sine half angle identity. And then for the cosine half angle identity, it's the same idea. So the cosine of x would be equal to plus or minus the square root of, and then usually we do 1 plus cosine 2x is usually how that's written over 2. So then for this, if I want the half angle, I would change that x to the cosine of x over 2 is equal to plus or minus the square root of 1 plus cosine, and this would become just x over 2. So this is my cosine half angle identity, and again, I just got that from my power reducing identities. So now I have my half angle identities, and the last one that we need to know is our tangent half angle identity, which is this one right here, and then these two are the other forms for the tangent half angle identities. And notice that in order to get this, we do sine over cosine for tangent. So notice that sine over cosine, we would have this over this. So your 2's and your denominator would cancel out. So 1 minus cosine x over 1 plus cosine x is how we get that. And then we can also simplify that into these two forms that we have right here. So you need to have each of these different forms memorized. So definitely memorize the double angle, the power reducing, and the half angle. There are some other formulas in this section that we're going to talk about, but I'm not going to require you guys to memorize them. These are the ones that I do require you to have memorized, so I'd start making flashcards and looking at them now. Now, if we look at number 1, it says use the subtraction and addition identities to find the sine of pi over 12. Well, we have done this a couple of times before. So what I would do is pause it and see if you can figure out what this is equal to, and then unpause it and we'll look at it together. So when we do this, remember we said we want to find the exact value of the sine of pi over 12, which is why we'd use the addition or subtraction identities to help us find that. So we have to think about things that add up to pi over 12 that are on our unit circle. So if I do 3 pi over 12 minus 2 pi over 12, I get pi over 4 and pi over 6, and then I'd use my subtraction identity for sine to get root 6 minus root 2 over 4 by plugging things into my unit circle. And I also did over here just to show you that if I would have done sine of 9 pi over 12 minus 8 pi over 12, that's pi over 12. So if I reduce that, I get 3 pi over 4 and 2 pi over 3 on my unit circle. And if I plug that into my addition identity, use my unit circle, and then my knowledge of simplifying fractions and multiplying them, I get the same answer, just in a different order. So same thing. Now we are going to find the exact value using the half angle identities. So instead of using the addition or subtraction identities, we can also use the half angle identities to help us figure out what the sine of an angle is going to be. So before we do that, I want to go back up to here and look at the sine of x over 2 and the cosine of x over 2. So for your half angle identities, the sign that's in front, so this plus or minus that we have, depends on what quadrant x over 2 lies in. So the sign in front of the radical depends on what quadrant x over 2 lies in. So we have to figure out what quadrant this is in order to figure out what my sign is going to be, plus or minus. So if I go back down here, pi over 12 I know is in quadrant 1. And if you didn't know, you could put it into degrees to figure that out. So if I want to use the half angle identity, I'm going to use the sine half angle identity because this is the sine of pi over 12. So the half angle identity for sine is sine of x over 2 is equal to, since it's in quadrant 1, sine is positive, so plus the square root of 1 minus the cosine of x over 2, because we talked about how to get that, we have it memorized. Now I have to figure out what x is going to be. So my original equation, we have pi over 12, and I'm trying to fit it into this x over 2. So the way that I do this is I set up a proportion. Pi over 12 equals x over 2, and we're trying to solve for x. So if I'm trying to solve for x, multiply both sides by 2. When I do that, I get x is equal to 2 pi over 12, so x is equal to pi over 6. That is what I'm going to use for x in my equation up here. So when I plug that in, I get the sine of pi over 6 over 2 equals the positive square root, because we're in quadrant 1, minus the cosine of, and we're not going to write x now, remember our x value is really pi over 6, so the cosine of pi over 6 divided by 2. So now I want to go ahead and simplify this. So this is equal to the positive square root of 1 minus the cosine of pi over 6, which is root 3 over 2 from your unit circle, divided by 2. And then of course we could keep on going. Now I want to simplify this, so the square root, and I always like to write the positive so I remember that I have it done. And I need a common denominator then right here. So what's common between 1 and 2 would be 2. So then I have 2 minus root 3 all divided by 2 divided by this 2 right here. Now remember, when you have a fraction divided by a fraction, because it's really 2 over 1, you're going to multiply by the reciprocal. So this is equal to the square root of 2 minus root 3 over 2 times, and the reciprocal of 2 over 1 is 1/2. And when I do that, I get the square root of 2 minus root 3 over 4. And then, of course, we can still simplify that. That becomes the square root of 2 minus root 3. And we're really separating this. Sorry, that's root 3 over root 4, which becomes 2. And I can't simplify the radical with the radical, so that's going to end up being my answer. An easy way to check this is to plug the sine of pi over 12 in your calculator, and then I would plug this into my calculator and see if the decimals match each other, which in this case they do. So that would be the exact value of the sine of pi over 12. And it's just a little bit different than what we had up here, but in the end it's still the same answer. It's just a different way of getting there. to reduce it. So let's try another one of these. If I want to do the tangent of 7 pi over 8, I have to figure out what quadrant is 7 pi over 8 in. Well, if you put this into degrees, you'll notice that this is in quadrant 2. So if this is in quadrant 2, then I know that my tangent in quadrant 2, if you think about all students take calculus, is going to be negative. So quadrant 2, the tangent is negative. Now for this tangent identity, remember the tangent half angle identity had 3 different forms. I don't like using the one with a radical if I don't have to, and I also rather prefer to have one term in my denominator rather than 2. So I actually like to use 1 minus the cosine of x over the sine of x. So that's what I'm going to use when I'm doing this. So now I need to figure out what x is if I have the tangent of 7 pi over 8. So the way that you do that is you take 7 pi over 8 equals x over 2. We're solving, in this case, for x by multiplying by both sides by 2. So when I do that, 2 times 7 is 14 pi over 8, and that reduces into 7 pi over 4, which is what's going to go into my formula for x. So I have the tangent of 7 pi over 4 divided by 2, because that's just my formula, equals 1 minus the cosine of 7 pi over 4 divided by 2. Now I need to use my unit circle in order to figure out 7 pi over 4. The cosine of that is root 2 over 2. So 1 minus root 2 over 2 divided by 2. Now I need to simplify this complex fraction by getting a common denominator. So this would be 2 over 2 minus root 2 over 2, all divided by 2. And that ends up being 2 minus root 2 over 2, all divided by 2. If I have a fraction divided by a fraction, because that's really over 1, I multiply by the reciprocal. So I get 2 minus root 2 over 2 times, in this case, 1/2. And notice that when I do that, I get 2 minus root 2 over 4. And then for this one, I think I'm missing. Okay, I didn't know, I forgot that I was missing the sine of x, so this should have been, that's my fault, the sine of 7 pi over 4, which is equal to negative root 2 over 2. So we're just going to add that in. This should be negative root 2 over 2. And then instead, this would have been, sorry about that. So we have 2 minus root 2 over 2 from what we got in our numerator, and then I'm going to flip this fraction here, so multiply that by 2 over the square root of 2, and then you'll notice that your 2's cancel out to leave you with 2 minus root 2 over root 2. Then we don't like to have radicals in our denominator, so I'm going to multiply that by root 2 over root 2. So when I do that, I have to distribute this to each of my terms here. So when I do that, I get 2 root 2 minus root 2 times root 2 is root 4, so minus 2 over, and again, root 2 times root 2 is root 4, which is just 2. And then this simplifies because I can factor out 2 from my numerator and my denominator here. So I get root 2 minus 1. And this right here would be my solution for the exact value of tangent 7 pi over 8. Now for number 3, and we're going to skip that one for just a minute and then go ahead and look at number 4. So for problem number 4, right here, it says find the sine 2x, cosine 2x, and tangent 2x. So it means find the sine double angle, cosine double angle, and tangent double angle, given that the sine of x is equal to 5 over 13, and we're in quadrant 1. So for this one, the sine of x is 5 over 13, and we're in quadrant 1, because that's what it says when it tells me that x is between 0 and pi over 2. So if I want to find the sine double angle, I use the formula 2 sine x cosine x. If I want to find the cosine double angle formula, I'm using cosine squared x minus sine squared x, or I can use one of the other forms because I know what sine is equal to, and I don't know cosine yet. And the tangent double angle formula, which is tangent squared x over 1 minus tangent, tangent 2 tangent x. We have 2 tangent x over 1 minus the tangent squared x. So for this, that means that I need to figure out what my cosine and tangent is equal to. So I can use my Pythagorean identities to do that, or I can use my triangle. So I'm going to go ahead and use a triangle. If I use my triangle, I know I'm in quadrant 1. Remember, we always make the triangle with the x-axis. Sine of this angle right here, remember, is opposite, which is 5 over 13. And that means I can use the Pythagorean theorem to figure out what the third length is going to be, because remember, we take, we'll call this side A. So a squared plus 5 squared equals 13 squared. So a squared is equal to 13 squared minus 5 squared. So a is equal to the square root of 13 squared minus 5 squared. So I know that a is equal to actually 12. So let's just use my Pythagorean theorem. And because of that, I know that the cosine of angle x then is my adjacent over hypotenuse, so 12 over 13, and my tangent of x would be opposite over adjacent, so 5 over 12. Now I can use those to figure out the rest of these, simplify these formulas. So for the first one, I have 2 times the sine of x, which is 5 over 13, times the cosine of x, which is 12 over 13. So remember, this is really over 1, so multiply all your numerators over your denominators. When you do that, you get 120 over 160. If I do the cosine double angle formula, I would have this is equal to my cosine 5 over 13 squared minus my sine squared, which is going to be, I did sines first. So cosine squared, which is 12 over 13 squared minus my sine squared, which is 5 over 13 squared. So when I do this, I can use my calculator, hit my math fraction key, and then do 119 over 169. And that was supposed to be a 9 for the first one. And then for the last one, tangent double angle, I'm just plugging it into the formula. So 2 times the tangent, which is 5 over 12, divided by 1 minus 5 over 12 squared. So when I simplify this using my calculator, I should get 120 over 119. And I didn't even have to use my tangent formula. If I know what my sine double angle is and cosine double angle, remember that the tangent double angle would then be equal to the sine double angle answer over the cosine double angle answer. So I could have taken these two solutions, divided them, and then got my answer. That would have worked as well. So bring this with you to class, and we will talk about the other two ones that we didn't get to. So we'll do problem number 3 and number 5 in class.